Hello. In this video, I would like to explain about the vector fields which we describe in vector analysis. The main objective of this video is to understand the concept of a vector field, to find whether a vector field is conservative or not, to find the curl and divergence of a vector field. So in this video, let us talk about the first two. That is, we would like to know what is a vector field, and maybe we will try to find out whether a vector field is conservative or not. A vector field is usually denoted by f bar, which is a vector. If it is in two dimensions, that is, it is over a plane, then it will be f bar of xy. So you may have a function in terms of xy multiplied by I plus another function in terms of xy multiplied by j. If it is a vector field over a solid, a three-dimension say, then you may have the vector field defined by f bar of xyz. So you'll have an I component, j component, and a k component. A very good example for a vector field is the gradient. The gradient is nothing but del f, where del is an operator. If in this example, small f, the scalar function is given by x squared plus y squared plus z squared, then the gradient will be del f, which is the partial derivative of f with respect to x multiplied by I, partial derivative of f with respect to y multiplied by j, plus partial derivative of f with respect to z multiplied by k, which will be 2xi plus 2yj plus 2zk, and this is a vector field. So the gradient of any scalar function will be a very good example for a vector field. These 2x, 2y, 2z are the I component, j component, and k component respectively. So the gradient of a scalar function is defined by del f, where del is an operator. It is a vector operator. I hat dou by dou x plus j hat dou by dou y plus k hat dou by dou z. So del f will be fx times I, fy times j, fz times k. So if you have a function like this, f of xy, x squared sine phi y, or z e to the negative xy, you can easily find what the gradient is by using the definition of gradient del f as I dou f by dou x plus j dou f by dou y plus k dou f by dou z. Suppose if a vector field is given in terms of its components m, n, and p. And if these components m, n, p, I, j, k components are functions of x, y, z, then those three functions must be continuous. And vector velocities or vector velocity fields, gravitational fields, and electric force fields are examples for vector field. Suppose if we are thinking about rotating a wheel, then the velocity will be acting on this wheel which is rotated in the direction given in the diagram. So those are all the tangents, those are all the vectors which are drawn. So it moves as if it is drawn in an anti-clockwise sense. When it is moved in an anti-clockwise sense, it is rotated that way. The gravitational force field will look like the diagram in the second figure, where all the forces will be focused on one particular point, which is the center of gravity. Let us see how to sketch a vector field. Suppose if a vector field f is given by negative yi plus xj, and if we are interested in finding the vectors, the gradient vectors for this vector field, we have to first of all project this on a level surface. After projecting this on the level surface, which is called the plane surface, then we can plot the vectors which will be of equal magnitude. So to get that level surface, the equation of the level surface is nothing but norm of the vector is a constant, because when it is a level surface, everything must be a constant. So norm of f is equal to c. Norm f is nothing but square root of negative y squared plus x squared, which is square root of x squared plus y squared, that must be c. Or you can say x squared plus y squared equal to c squared, which is nothing but a circle. This is a circle with center at 0, 0 and radius equal to c units. So as we change the value for c, this x squared plus y squared equal to c squared will give a family of curves where the center is at 0, 0, where the radius increases, say 1, 2, 3, etc. So if we are trying to draw or sketch the vectors, the gradient vectors for this vector field, let us take one flat surface, that is on the plane. We know that we have family of circles. So let us talk about the center circle, the unit circle. The unit circle is the circle with center at 0 and radius equal to 1 unit. That just this circle alone. For this circle, let us take those 4 points, say 1, 0, 0, 1, negative 1, 0, and 0, negative 1. At these 4 points, we can find the value of the function or the vector function capital F bar, and we get that as j, negative I, negative j, I. So at the point 1, 0, you can draw the vector which is a unit vector in the positive direction of the x-axis. And at the point 0, 1, you can draw a unit vector not on the positive side of the x-axis, it is on the negative side of the x-axis because it is negative I. So this is your negative I. So you have an arrow here. The same way, at the point negative 1, 0, you need negative j. So it is opposite direction of j. So this is my negative j. And here I have positive I. So it looks like these vectors are drawn on this unit circle, and it looks like they are all in the anti-clockwise sense. Now if we are trying to find the vectors or for the whole complete vector field which are drawn in the level surfaces, that is, you are trying to take all possible family of curves, circles, and for all the circles, if you are trying to draw the gradient vectors, then the diagram may look like this. You can easily get these diagrams using the computer-aided softwares like MATLAB, Maple, or Mathematica. Next, let us talk about a conservative vector field. Not all vector fields are conservative. Only few vector fields will be conservative. So let us see what is the definition of a conservative vector field, and is there any easy test to verify whether a vector field is conservative or not. The definition says that a field F bar is conservative, vector field F bar is conservative if you can find a potential function small f such that f is equal to del f. If you can find a small function f such that capital F bar is del times f, the gradient of f, then you can say that it is a conservative vector field. Now let us take this example. suppose if capital F and small f are given, we can check whether it is conservative or not. Since small f is there, we can find the partial derivative of f with respect to x, partial derivative of f with respect to y, and we can find the gradient del f, where del f will be 2x times I plus half 2y times j, which is yj, which is nothing but our original function f bar. So since your vector function f bar is del times f, you say that f is conservative. This is the second example where a function capital F is given, which is your vector field. A potential function small f is there. You can verify whether it is conservative or not. So del f will be given like this. You find the partial derivative of f with respect to x, with respect to y, and with respect to j. Make use of the definition of the gradient, and you can say that this is nothing but k times u divided by r squared, where u is r by r, norm of r. Therefore, your f bar is conservative. There is another test to check whether a vector field is conservative or not. If it is given in the component form mi plus nj, and if we are not aware of any potential functions, any small function f, then by using this partial derivatives, if you are verifying if dou m by dou y is dou n by dou x, then you can say that it is a conservative vector field. This is the case when it is on a plane surface. If it is with only two variables x and y, you'll have to verify whether dou m by dou y is dou n by dou x. If you have got a vector field in space, then you may have mi plus nj plus pk. In that case, you have to verify whether dou n by dou x is dou m by dou y, dou n by dou z is dou p by dou y, and dou p by dou x is dou m by dou z. If all these three equations are true, then you can say that the vector field f bar is conservative. In this example, f bar is x squared yi plus xyj. You can check whether it is conservative or not by making use of the second test, because the small function f is not there. So you find the partial derivatives with respect to x, y, and then see whether it is true or not. In our first case, the partial derivatives dou m by dou y and dou n by dou x are not equal. So since it is not equal, it is not conservative. In our second example, the two values are equal, therefore it is conservative. You can easily verify whether the vector fields are conservative or not for these three questions. And also you can easily check whether 21 to 28 are conservative or not. And also you can check whether capital F is conservative or not. So for the first set of problems, you use the definition of use method 1. For this, you use method 2. Hope this video was useful. Thank you for listening.